All right, recording is rolling. Welcome to Wednesday, October 25th. Yesterday, with the substitute, I had you guys filling out as much as table as you could. Back when I saw you on Monday, I did these two rows with you. We were looking at a new topic, energy and energy conservation. So you were using this framework and just choosing here. This was like your equation bank right here, expression bank, right, to piece together these formulas. We're going to go over the answers to those today. Well, we'll go as far as we can, right? Not the last couple rows. There's a couple labs coming up pretty soon. Due dates coming up. So AP classroom for AP students, of course, Monday morning because I want to go over the answers to those. Then I think by this weekend, you guys will be able to do those. Textbook puzzles aren't due until next Friday, so about a week and a half from now. Right. So let's take first few minutes to do a recap because back last time I saw you on Monday, it was really introduced to a new topic, right? New unit. Right. So energy and energy conservation. So this is a new framework for thinking about things, and you can use to set up and solve all sorts of problems, including all 12 examples in this packet, right? Right. So energy is something that you can't create or destroy. Right? Kind of like maybe in chemistry you learn about conservation of mass. This is a similar type thought process. Conservation of mass you can use to set up like stoichiometry equations stuff, right? So here I got conservation of energy, right? Sum of energy initial equals sum of energy final. That's true for a closed system. A closed system, you could say if there's no energy entering or leaving that system. Another way to say it is there's no work done on or by the system. That's kind of the same thing, just rewording, right? Another framing, sometimes we'll say there's no external force on the system, right? An external force for some distance, right? Right. Now there are, in this right here, most of the examples in this packet are some version of those closed systems, right? Now you might have an open system where you start off with sum of energy initial, start off with some energy in the system, and you either have work done on or by the system, so you could add or subtract some amount of energy. That's what work is, right? It's a transfer of energy, right? So you end up with some different amount of energy. Now these are all in joules, right? Joules, right? Like 1 joule breaks down to 1 Newton times 1 meter. Right? There's just a couple of examples of open systems that are on this packet, right? Right. Now, what's going to feed into each of these? Because sum of energy initial, sum of energy final. Okay, that's really generic, right? But here's the expressions you care about for this class, right? So work could be force times distance, like on something for some distance. That's a transfer of energy. Okay? Potential energy, right? Mass times gravity times some height that it could change or height that it could fall. Right? Energy stored in a spring, right? Which is a form of force times distance, but it's a variable force. I talked about this on Monday. It's all a recap, right? So the more I pull it, the more force that takes. And if you know the spring constant, okay, 1/2 kx squared, x is how much you stretch the spring. There's energy of motion. If something's in motion, has some mass, has some speed, right? 1/2 mv squared. Right? Those are the main four that you care about, right? These gold boxes here. Now there are a couple of green boxes that's well, a little bit more abstract. Talk about these a little bit, but most like 95% of the time you just care about these four gold boxes. Right. Right, let's look at the two that we solved back on Monday. So go recap. Right? These are really fundamental classic examples. Both of these are. If you guys take physics in college, then like for sure you're going to see like both of these examples. So how about Galileo drops the ball, and how fast does that ball crash land? Right? Which you do have a way to solve already. Like I could have asked you guys this question weeks ago, and you could have figured out the crash speed is square root 2gh. You would have just used this third kinematic expression right here. Right? And that's something you'll see a lot with these conservation of energy equations. A lot of these, not all of them, but a lot of them you could solve using other parts of physics that you know so far. This is just a new framework for thinking of it. And the new framework is, well, at the top, it's all potential energy. So you call it MGH, energy due to position, due to height. Right? Right before it crash lands, it's pretty much lost all its height, but if it's moving really fast, it has pretty much all this kind of energy. Right? Energy of motion, 1/2 mv squared. You can equate those two because it's a closed system. We're going to say air drag is negligible. Right? The mass of the ball cancels and the speed is square root 2gh, right? Just like you would have gotten with the kinematic approach. Right? The other one we did back on Monday was this car break to stop. And I want to look a little bit more at this one day because I do have a poster for this, which matches what we did, right? But there's so much more stuff I wanted to say, but just ran out of time back on Monday. Right? So this is going to be an open system. The idea is that we're just focused on the car, right? Right. So just if I only focus on the car, there is an external force that matters, and that's the friction force on the road. The friction force is actually slowing it down. Right? That's why it's an open system. It's an external force. Right? Versus like the Galileo dropping the ball. If you include with the both ball and the Earth, then all the forces are internalized. But here, it's just the car. There's an external force. Right? So the car's going to start out with some energy. It'll be all energy motion. There's your 1/2 mv squared. Right? But it ends up with zero mechanical energy at the end, right? Because there's no motion. It didn't go up any hills. There's no potential energy. There's no springs. Right? So where did all the energy go? Well, it didn't disappear from the universe. Right? It went into friction on the road. So that's some kind of force times distance. Right? Here, go back to that checklist of, where's my checklist? Oh, there we go. Right. Some kind of force times distance. In this case, a friction force. And you're subtracting because it's pulling energy, mechanical energy out of the system. It's just the car. Okay. Right. If you put a thermometer on the road, maybe the road heats up a little bit. That's like thermal energy, right? Which is not on this list, right? I mean, there's a bunch of energies, types of energy, forms of energy that are not on this list. I don't say anything about chemical energy in a AA battery. I don't say anything about thermal energy. I don't say anything about nuclear energy, right? Right. So just mechanical energy. Mechanical energy, I just care about, again, like mainly these 4 boxes right here. Okay. Right. So here we go. Here's the setup. 1/2 mv squared initial, right? Subtract out the friction force times the stopping distance, and you'll get to 0 joules if it breaks completely to stop. Stop means 0 mechanical energy. Right? Okay. If you like, you could do the substitution. Could you guys say friction force is coefficient of friction times the normal force? For example, if friction force is half of the normal force, then you say, oh, well, the coefficient of friction must be 1/2, right? So that in there. And then the normal force is just equivalent to the weight as long as it's a flat road and there's nothing crazy going on, right? So I did like a double substitution right there. You guys see that? Right? From this line to this line. Right? Then, guys, what cancels out at this point? What variable cancels out? The mass of the car, which you might remember we kind of talked about a car breaking to a stop a few weeks ago, and that was the same thing. Here, I'll show you guys that force poster here in a minute. Let's finish this first, right? The mass of the car does cancel out, right? And then usually the classic question is how far does the car break, or what does that have to do with anything else, right? So usually this is how you solve this. You say, well, the stopping distance is, and then it's this expression right here. Here's the initial speed of the car, coefficient of friction, gravity of the planet. Right? Okay. And the main relationship, again, like usually the question is the relationship between these 2 variables. Braking distance is a function of the initial speed of the car, right? And I pulled that relationship out right here, right? That's that proportional relationship. So let's see if you guys can navigate this. Suppose you're in a car, you drive, brake to stop, okay, great. And then you go back and you do exactly the same thing, except that you're going 3 times as fast initially. Guys, if you triple your initial speed, what happens to your braking distance? It's longer by how many times? 9 times, right? Because a factor of 3 squared, right? If you're ever not sure, you can just make up numbers playing. Well, what if I have a 1 kilogram car and it's going at like 10 meters per second? Go 30 meters per second, right? Plug in the numbers. You get factor of 3 squared is like 9 times the distance. That's probably pretty good to know, right? What if you're driving around, right, and you like double your speed? How much more road do you need to brake to a stop if you double your speed? Is it double the road? No, it's how many times the road? What's 2 squared? Be 4 times braking distance, right? So that's a really classic physics question. Okay? Where you guys kind of saw this before. Oh, whoa, I thought I had that poster lined up. Where? Oh, all right. This one here. Here's the old take on this, right? You could have answered that question before. What's the braking distance? And this is like the first half of it. Here, we've got the orange banner because this is like a dynamics point of view. I had you guys go through and say, what's the acceleration of the car? Now, this context, acceleration is the rate that it's slowing down. So maybe this could be a negative value, right? Rate of car slowing down, right? Free body diagram, substitutions, blah, 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 right? But here, the mass of the car also canceled out, right? Just like it did for the energy point of view, right? And then the next step would be from this, once you got that acceleration, then you could just plug it into this third kinematic expression right here, right? Fit right there. This would go to 0, and then you would get the same answer that you get from this energy approach. You'd still get this exact same answer right here. Okay? Just be now you guys have more options. You guys have more ways to solve things, right? Right. So you guys good so far? All right. So let's go on down the list here. Hopefully you guys were able to knock out a bunch of this packet, and you'll be just checking your answers today. And hopefully you got a lot of these right. So this scenario: cannon fires a cannonball at some angle from ground level, right? I remember a few weeks back we were doing projectiles. You guys remember projectiles? Right? You might get this exact question. I'd probably throw in the detail of like, what is this blast angle? You say, well, I'm going to break that into components and figure out how much time. Right? It'd be like a whole process. Right? But here we're going to do a little bit different approach. Right? should lead to the same answer, regardless of how you solve it. Right? So point A is it's already left the cannon barrel, right? It's already in motion. And point B, maybe it's like maximum height would be a good spot something out. What do you think is internalized in the system, like a closed system? The what and the what? The cannonball we're focused on, right? It's like change in speed. It's like slowing down on the way up, right? Oh, and the fact that it goes through some height change, I should also include the what? The Earth. Yeah, there you go. Yeah, so we got them both. Yeah, the cannonball and the Earth. There you go. Right. Okay. Anytime you see a height change for a conservation of energy setup, yeah, you're going to include the Earth and the closed system. See, if I didn't include it, then the weight of the cannonball would be external to the system. But if I include the Earth, okay, right, now the plunge. Okay. Right. What type of energy at point A? And here's your checklist to choose from. Right. So it's just like the cannon barrel. It's basically at ground level, but it's moving really fast. Yeah, 1/2 mv squared. It's all kinetic energy. Let's go 1/2 mv squared at point A. Right. Now, when it gets to point B, ooh, it's been lifted some height, which is what type of energy? MGH. Right. Point B, right. But it's probably also in motion. I mean, unless you blasted it straight up and you're looking at maximum height point, just in general, it probably has some energy left over. Okay, call it or for kinetic energy, right? 1/2 mv squared, and that's at point B, right? Something like that. Sure. Okay. Right. So, big picture, this is equal to these two because closed system. Right? Suppose I gave you some numbers, like I'll give you the mass of the cannonball and the blast speed. You put it all together. Just for example, what if there's like 1,000 joules here, and maybe 300 joules went into lifting it up to that height, and the other 700 joules is left to go into its speed, right? Or kinetic energy, you can calculate the speed, right? So 1,000 equals 300 plus 700, right? If you had numbers to feed in. We're going to solve in terms of variables. Right? That's a good skill to have, right? Solve in terms of variables, you get these universal answers. You can plug in any masses and any speeds and any heights and right? So here's our framework. Sum of energy initial equals sum of energy final. If you ever think you have to do an energy conservation, especially if it's an FRQ, like write that as your first step. Like that's the framework that's going to solve this. Okay? Then we have 1/2 mv squared, little subscript a on that v, right? It's just like the cannon barrel, right? And then by the time it gets to point B, well, it's been lifted against gravity, so mgh point B, right? And then whatever's left over is left for kinetic energy, 1/2 mv squared, and that's at point B. Or we're solving for what is the speed at point B, right? That's perfect. Right? All right, and now the dominoes are starting to fall. We just got to do some algebra to solve for that vis-a-vis, right? Ooh, guys, I got 3 terms, boink, 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 3 terms. Is there a variable in common that can cancel out? Yeah, the mass of the cannonball, right? In fact, if you were thinking, I could solve this with projectile motion, that was kinematic. We were never even dealing with masses back then, right? So yeah, so it totally makes sense that cancel out the mass, right? And what's that? Okay, yeah, that's gonna be another thing. At some point, I'm gonna multiply everything by 2, right? Yeah, let's do it. Let's multiply everything by 2. VA squared. So this is just algebra at this point, right? 2GHB plus VB squared, right? Looks like I do a couple other things. I gotta subtract this term over and then take the square root. Okay. So VA squared minus 2GHB equals VB squared. All right, and then finally take the square root. Okay. So I got a big old square root. Got b sub a squared minus 2gh. Okay. That's hopefully what you came up with yesterday. Right? Oh yeah.
Isn't that a third column equation? No.
Yeah. That's a good observation. Look at that right there, right? That is that's pretty much a rearrangement of this guy right here, isn't it? Yeah, right. Interesting to note that back when we were dealing with this, we were kind of strict about like make sure everything was in the same directions, whatnot, right? Like especially these first two, right? Is it strictly up or down? Is it strictly right or left? Kind of, right. But that is kind of a funny thing about the third one is that now that we're off to this energy section, energy is scalar, so we don't really care about direction so much, right? Kind of interesting that it's like, oh yeah, looking back, I guess these speeds, you could treat this as speeds and the direction never really mattered, right? You could blast a cannonball off at some whatever 33-degree angle, right? Yeah, so that's a good observation right there. Okay. All right, so there's our answer. So over here, I'm just going to do dot, 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 because we solved it over here. I'm going to say v at point B equals, I got a big old square root, VA squared minus 2GH. There you go. Okay. Oh, I should too mention, look at how you wrote your answer. Right? Did anybody write anything that looks like this? Equals square root VA squared minus 2GHB. Right? Guys, what's wrong with the way I just wrote it down here? Yeah, you have to communicate to whoever who's reading your work, like what you're taking the square root of, right? You don't want to like prematurely injure square roots, right? You got to extend this over the entire inside expression, right? And maybe sometimes drop this down where it matters, right? Got to make sure it's all underneath that radical, right? I'm just pointing that out because over the years or even this year, I've seen a lot of students just kind of stop their square root like way too early. Right? Another thing good to do is like once we got our answer, just focus on that. Okay. Say maybe play around with this, poke around with it, plug in some numbers. Say, does this kind of make sense? Play around with some variables. Compare this to other things we know. Does it fit any patterns? Okay. So I remember Galileo dropping the ball. The speed was square root 2gh. Right? And look what we have here. We have square root. We have a square root going on. We have like a 2gh going on. At least it kind of fits that pattern. We're subtracting this case, but that makes sense, right? Because the higher the ball goes, the slower it's going to be going. Okay, so it does make sense we'd be subtracting that. Okay. Oh, look, the faster the blast speed, the faster it's going to be going at point B. That makes sense too, right? You guys see how it right? Makes sense and is consistent with what we've done so far. Right, very good. All right, next one. We've got a kid in a sled sliding downhill, and there is friction, right? This is the only other open system example I have on this whole table. Right? So just these two right here. And all these other examples are just going to go back to being closed systems. Okay? Right, this is the only other open system. And so I want to have the kid and the sled definitely as an object in the system. Right? I'm also going to include the Earth. Right? Now, if I just include those two, then there's still a friction force from the surface, which is an external force. That's why it's an open system. So I'm going to treat this as an open system. Right? Now, at the top of the hill, what type of energy? Yeah, MGH. Right? And then, isn't friction acting on that system the entire way down? And it's like pulling energy out of this kid sled system? Yeah, minus the friction force times the length. I'll call it L because it's actually over that length. Okay. And then at the bottom, well, at the bottom, there's probably no more potential energy, but it's probably motion, right? Probably some speed down there. You guys think there is what kind of energy at the bottom? Yeah, kinetic, 1/2 mv squared. There you go. Where m is the mass of the kid and the sled together. Right? This would be point B. Right? Maybe we're like solving for that. Right? So I'll go sum of energy at point A minus the work done by friction leaves you with the sum of energy at point B. Okay. At point A, just like you guys said, it's MGH. Okay. Do minus friction force for like force times distance. That's what work is, right? And that'll leave you with some 1/2 mv squared at point B. Right? Joules, joules, joules. Right? Maybe he starts off with, just make up some numbers, like 1,000 joules at the top. Maybe he lost like 500 joules to friction, and the other 500 joules are left to go into his motion. Oh, yeah.
Would you be able, is it logistical to expand friction force into friction coefficient?
Yeah, you could do that. Okay. So, yeah, how you actually finish this off, it's kind of up to you. I just really want to get the fundamentals down here. You could do that, right? So, I haven't been doing that all day today, but since you brought that up, let's go ahead and do that. Okay. Earlier today, I've just been solving it from here, just solve for VB, right? Let friction force. But if you like, you could make that substitution. You could say friction force, could that be coefficient of friction times the normal force? And is the normal force just mg cosine theta? Right, where theta is talking about this angle theta right here, right? And then, okay, still got L, then 1/2 mvb squared. And there's an advantage to doing that. And the advantage of doing that is I have 3 terms that now all have the m, and you could cancel out the m at that point. So that's true. Okay. Here, may as well just got it at that point. Okay. Again, remember the class. if you're watching this video at home and thinking, we didn't do that in my class, that's okay. It's a little bit different ways to think about this, right? Then I need to multiply by 2 and then take the square root, basically, right? Times 2 and then square root. Right? So the speed at point B will be, okay, so I'm going to have a big old square root to end this whole thing. All right, got a 2gh, and then minus, and then a 2 mu g cosine of the angle, something like that. Right? Where mu is the coefficient of friction. Right? Okay. That should do it. Right? So write that in this box, dot, dot, dot. Then say the speed at point B is, and it's going to be a big old square root, 2gh at A minus 2 mu g cosine of the angle. That's all underneath that radical. There you go. Just that. Okay. So yeah, before we skip on to the next one, let's pause and take a look at this and just make sure that this does make sense. Right? Like, what if we actually changed the premise of this a bit to make it a frictionless surface? Like the coefficient of friction goes to 0, like an air hockey table, right? What if we turn this into a giant air hockey table and put a puck up there and then tilt the table? This thing slides down with 0 friction, right? Guys, if there's 0 friction, what happens to this whole term? It just goes away, okay? And then the speed then is just the square root of 2g. Square root 2gh. That's the same thing as like Galileo dropping a ball off a tower. Kind of interesting that it also has nothing to do with the angle of the air hockey table, right? Like this angle theta, this could be 2 degrees, 5 degrees, 10 degrees, 45 degrees, 80 degrees, 90 degrees. It has nothing to do with the answer of how fast it's going to be going at the bottom. Again, with no friction. If there is friction, that it changes. But if there's no friction, it's just square root 2gh. Okay? Now, if it's like a 2-degree angle, you've got an air hockey table, a 2-degree angle, that air hockey puck is slowly accelerating down. It might take it like a long time. It take a whole hour to get to the bottom, but by the time it gets to the bottom, it's still going square root 2gh for its speed, right? As if Galileo just dropped it straight vertical. Interesting thing about right? And then if there is friction, oh look, the greater the coefficient of friction, the more energy is being diverted to friction, the slower it's going, right? And then I guess the smaller the angle, well, cosine of small angles gets closer to 1, right? Okay, so it's like an angle trade-off too, right? Think about that. All right. So that checks out. You guys good so far? All right. So the rest of these are all closed systems. Okay, nice. All right, next one. Got a spring fires the block mass M onto a frictionless track. So taking a block and then let go, and fly around. Okay. What did you guys put for what's in the system? Exactly. Yeah, the block, right? Because it's changing speed. We need to focus on that. The spring, because at the beginning, all the energy is stored in the spring. And yeah, the earth, because the block changes height, so it's going against its own weight. So there's a force going down. Right? That's a good question. Do you include the track? Okay, here's why I'm not including the track. Oh, since there's no friction, then there's no friction loss from the track. Right? Now, there is a force from the track. Guys, what type of force? There's a name for it. Starts with an N. What type of force from the track? The normal force, right? Right. And remember, there's no friction now, right? But there is a normal force. But that normal force, isn't it always perpendicular to the motion of the block? So if you do force dot distance, like as a dot product, what's the dot product of any two perpendicular vectors? 0, right? Because remember, dot products, force times distance, you only multiply the parallel, right? Yeah, so the track doesn't actually do any work on the block, right? So yeah, so I just see the track out. That's a good detail to, if there was friction, I would have to consider that. Right. Energy at point A, what type of energy at point A? Yeah, spring potential, that's your 1/2 kx squared. K is the spring stiffness, spring constant. And then X is how much you smashed it, like compressed it. Right, so now it's spring load, ready to go. Oh no, that's such a good video going too. Well, okay. Yeah, let me pause this and figure out what. Okay, recording resume. I think we're just gonna shelter in place and let's get as much as we can here. Right, so by the time it gets to point B, I think the energy went a couple of places. Where and where? Do you have to lift up this height? And what's the expression for that? MGH, right? But it had to, like, to get to that point, it did have to like go around this loop. So I bet it has to have some speed up here, which means that it has energy and motion. And then I'm going to express that as what? 1/2 mv squared. So point B, right? And then this table set up to solve for the speed at point B, right? Okay, so that here's like the source of energy, and here's where it went, like supply and demand. Okay. So for example, suppose I give you some numbers and you plug them in, and it starts with like 100 joules here, and then it took like 30 joules to lift it, and the other 70 joules go into its motion, right? So 100 equals 30 plus 70 in terms of joules, right? And then if you knew the mass of the block and these other numbers, you could do a little algebra and solve for V. But we're going to do one better. We're going to solve in terms of variables. So we're going to get a universal solution. So sum of energy at point A equals sum of energy at point B. At point A, it's all 1/2 kx squared. At point B, well, now we got this mix of mgh plus 1/2 mv squared. So little subscripts on these, right? We're solving for this VB, okay? Right, so we can definitely get that. We just got to go through an algebra process, subtract that, times 2, divide by m, square root. That's the algebra steps we're about to do. Okay? Okay. Pause for a moment. Does the mass of the block cancel out in this case? You're right, it does not. Okay? Let's see if that actually makes sense, though. Like, what if I'm comparing these two masses? So if I smash this against it, that's great, let go. Fly around crazy fast. What if I smash this guy spring and let go? Think it's going to go a lot slower? Okay, yeah, so it definitely makes sense that the mass would not cancel out. I hope the proportional relationship is also correct at the end of this, but let's find out. So subtract over the mgh. So 1/2 kx squared minus the mgh equals 1/2 mv squared. Right. Just gonna multiply everything by 2. Kx squared, I'll just go ahead and divide by m while I'm at it. Kx squared on m minus 2 mgh on m equals v squared at point B. Okay. Then last step, take the square root. So the speed at point B it's a big old square root. We got kx squared on m minus 2gh.
And with the shelter in place, thank you for your cooperation. That was a false alarm in the new building. Again, thank you for your cooperation. We are lifting the shelter in place.
Ooh, all right, new building on fire. All right, no, we're all good. All good. All right, so I'm getting this. Again, if I gave you guys numbers at the very beginning, you could have plugged in numbers and done the same algebra process, just numbers. Okay. Okay. Right, but we got we did even better. We got the answer in terms of variables. Right, so let's look and see, does this make sense? So, I see something about V being like square root 2gh, kind of like the Galileo problem, but it's subtracting, which makes sense because the higher it goes, the slower it's going to be going. Okay.
How would you make two separate functions? Maybe dividing by n. Like, why don't you just put kx squared minus mgh over?
Oh yeah, you could take this whole thing and then all divide by m. Okay. Yeah, you could do it. Okay. Yeah. Yeah, I did break it up into 2 fractions, which is also okay, and then it cancels out with 1, but not the other. Yeah. So m is still in the final expression. You could have 2 mgh over here, and then that all divide by m as a giant. Yeah, that'd be another way you could do it. Right? And if you did it that way, if you wrote something like dv equals square root kx squared minus 2 mgh, all collectively divided by m, okay, they would accept that too. That would also be a correct answer. So do that. Yeah. If you did that yesterday, then that's 100% correct. So, okay. It looks like the stiffer the spring, the faster it's going to go. Check. Looks like the more you compress the spring, the faster it's going to go. Check. Right. It looks like the more massive the block, the slower it's going to go. Ooh, that makes sense too. Right. So BB equals, because we just did all the work here, giant square root, kx squared on m minus 2gh. All right. Next one, bungee jumper dives off a platform and barely touches the ground before the cord retracts. So the story might be like he dives off, he's falling, he's in free fall for a little bit, and then that cord starts to stretch, right? And then he's getting like, oh, I'm gonna crash, and then right as he's about to hit the sidewalk below, you like reach out, point touches it, and then the cord pulls him back. So he's all right. Okay? I'll tell you guys where I got the original inspiration for this one. This was an FRQ back in the day. This was an AP FRQ. Actually, they asked a more complicated version of this because they told you some total height. They told you the length of the bungee cord. They told you how much the bungee cord stretched. Like you had specific numbers with it. So I'm actually giving you guys a more fundamental version of something that AP has asked in the past, like, as an FRQ, right? Do you think we're going to treat that bungee cord basically as a spring? Do you guys think? Yeah. Okay, so you guys figure that out? Okay. What should I include in the closed system? What do you guys think? Yeah. How about the bungee jumper? How about the cord, right? Which we're going to basically treat like a spring. Right? Ooh, and also I should include the earth, right? Yeah, because there's some gravitational pull, right? If you change the gravity field, I bet that get a different answer or something. Maybe it's stretched differently. Okay.
Would you go like that to say like bungee jumper, cord, earth, and then cord again? It's like doing the opposite again.
Oh, well, you can just include the object one time. Yeah, I don't think the order exactly matters too. So yeah, you can list them in any order. All right. Yeah, the important thing is to list the objects that like if there's any force between them, it's all, and the forces are all internal. Yeah, so there's no external forces. All right. Energy at point A, there's definitely what kind of energy? Yeah, potential energy, MGH. Okay. Now here's where maybe there could be slightly different answers depending on how you interpret it. It's okay. Right? You guys see that word dives off, right? Now this could make it more complicated or not. Right? If you just had MGH yesterday and you solved it, that's fine. I'll accept that. Right? If you look at that word dives and say, well, maybe instead of jumping or instead of stepping off, what if he does like a running jump, like whoa, like jumps off some speed? In that case, he would also have what kind of energy at the top? Yeah, 1/2 mv squared, right? So if you solve this and you didn't include that's okay. But if you did, then maybe it's go a step deeper, right? If you know like how fast he runs and jumps off, right? Right. By the time he gets to point B, what type of energy there? Yeah, 1/2 kx squared, and nothing else, right? Because he's basically at ground level, has no more gravitational potential energy. There's no kinetic energy because he's not in motion. He's like turning around. Yeah, right. So that's it. That's the setup. It's a closed system. So that equals that. And so what's the speed at? Oh, yeah, guys. What is the speed at point B? Yeah, 0 meters per second. We don't need to do anything, right? That's probably not the question they would ask you, though. Right? The question they could ask something like, maybe if you know the properties of the bungee cord and like how much could it stretch, or like what height could he jump from, or they could ask anything about these variables, or they might do a proportional thing, right? If he's like twice as massive, or if he has a friend who's twice as heavy, right? Then how does that change something like that? Okay. All right, you guys ready for these Atwoods? All right, so we're starting with the modified. It's a little simpler than the classic. Right? So modified. Oh, there's no friction. No friction. Hey, when you guys did this version, you guys remember how do you guys slip a Hot Wheels car right there? Add some little wheels right there. Basically, get rid of the friction. Or air hockey table if you like that story. Right, so this thing's kind of like that. I'm thinking 3 objects in the system, in the closed system. What are the 3 objects? Yep, both the masses and the Earth. Yeah. So AP might call this an M1, M2 Earth system. Like that. Oh, speaking of naming systems, I forgot a little detail. Let me jump back a little bit before we get too carried away. Right. This one at the top here, this one at the top. Did you guys notice that that's nearly identical to this? Right? The track looks a little bit different, but the equation setup is exactly identical to what we just did 2 examples ago. Right? And it's called the something system. Right? Okay, all right. Let's get back to Atwood here. Atwood. All right. So, curious to see how many guys have solved this. What did you guys have as the source of energy that's driving all the motion? Yeah, and what expression is that going to be? MGH. Now, which mass are we talking about? Yeah, mass T, right? You guys see how mass T is hanging over the edge? Mass. Yeah. You guys see what's going on, right? The fact that mass T can fall, the fact that mass T undergoes some height change and Earth's gravity is pulling it down, right? That's what's driving the whole system to move. That's like the supply of energy, right? And that energy is going to go to two places I'm looking for. 2 places. What are they? Where does the energy go at point B? Yeah, kinetic. We got 1/2 m1v squared plus also 1/2 m2v squared. Right? Each of those boxes has a kinetic energy. block 2 has basically no potential energy at point B. Let's say it's like 1 millimeter above the floor. So it's pretty much lost all its height. It's pretty much, right? And then we're going to solve for what is the speed at point B, right? Now, how many guys are looking at this thinking, solve for the speed, right? Thinking, hang on a minute, I think I could actually solve this before we even got to energy. I could probably solve this last week, right? If you solve for the acceleration, which you guys solved back in your lab, you guys solved the acceleration system, and then you jump back to kinematic motion and say, well, if it undergoes this distance change, which, right, you could solve for the speed that way. You guys think? Right? Let's do both ways. We're going to do 2 different solutions side by side right here. We're going to solve this through dynamics and kinematic motion. Right? And then we'll do the new way through energy. Right? We'll do each one of these. Do this way, do this way. Right? To solve for the speed at point B, we should get the same answer though, right? So the old way of doing it, I remember the acceleration of the system, well, from a systems point of view, couldn't it be Newton's second law of motion, net force on total mass, right? So that would have been like the hanging weight divided by the sum of the masses. And then you go back to kinematic motion, say, I want to solve for a speed given some distance. That's this third kinematic expression right here. Bring that guy in. So I'll go final velocity squared equals initial velocity squared plus 2ax. Right? This v naught 0 if it starts from rest, that goes with, and the acceleration is that right there. You guys do remember this being the answer to that modified outward, right? For 0 friction. Okay? It's a good one to know. Good chance you're going to see that on the AP exam. Okay? So let's plug that in. And then one last step here, I'll just do this right here, is just take square root. Right? Square root. So the final speed, which is the speed of point B, is, okay, what's going to be a big square root, because that's the last algebra step. You got 2ax. So it's 2, acceleration is m2g divided by the sum of the masses. And I got an x up in the numerator. Okay. There you go. Okay. So the old way of doing it, oh, yeah, thank you. Okay. The old way of doing it, this should be what the speed is, right? But now we have a new framework. Now we're going to do the sum of energy at point A equals the sum of energy at point B. And we've already identified what types of energy are where. So I'm just going to plug those in. I say M2GH is providing the energy, like the supply of energy. Okay? And that's going to go into, but by the time they get to point B, now they've lost all the height they're going to lose, right? I got it at 1/2 m1v squared plus a 1/2 m2v squared, just like that, right? That's the energy setup, isn't it? That's just what we did right here. I'll just say equals, boom, boom. Yep. Yeah. All right. All right. Maybe I'll factor out a 1/2 v squared from the right side. So m2gh equals 1/2 sum of masses v squared, like that. Okay. Multiply both sides by 2, divide by the sum of masses. So 2 m2gh divided by the sum of masses equals v squared. Okay, and last step, take the square root. So the final speed, the speed at point B is, okay, it's going to be giant square root. We got a 2 m2gh all divided by sum of masses. Right, the square root bar extends over that entire inside expression. Whoa, look at that. It's the exact same thing. Well, I guess one of them called H and the other called X, but it's the same thing, right? I mean, X is H in this case, right? All right. So now you guys got multiple ways to solve that question. If this was an FRQ, you could solve it this way, or you could solve it this way. Right, so BB equals, got a big old square root, 2 m2gh all divided by m1 plus m2. We could play around with those too. Like, for example, here, let's bring up the larger version. Right? For example, what if this m1 was 0? Like you have a hanging weight and you just have an empty string over here. Would that pretty well a free fall? Right? Just pure free fall, right? and what would that look like in the expressions here? Pick either one, they're the same thing. If M1 goes to 0, then this zeroes out. Oh, M2 over M2, does that cancel out? It would. And you'd be left with the speed as the square root of just 2gh. Oh, which is exactly what it was for Galileo dropping a ball off the tower. Square root 2gh, right? So, okay, so that's good. That's good. It's consistent with everything else we've done so far. Let's do the classic Atwood now. Classic Atwood. Do you think it's still think it's M1, M2 in the Earth? So what you guys got for the closed system? All right, now this one's a little trickier, but not that much. Right? What do you think is supplying the energy for this whole thing to move? Yeah, what expression goes right here? You're gonna write one term. Right? Or let's suppose it starts from rest. I didn't explicitly write that, but suppose it starts from rest. If it starts from rest, it doesn't start off with any kinetic. Right? Guys, can something fall down? Can something fall down? Is that supplying the potential energy? So what term? M2GH. Yeah, right? The fact that the larger mass can fall down is going to drive the whole system to move, right? And now that energy is going to go to 3 places. 3 places. What's one of the places it goes to? Okay, so something about actually that's 2 of the places, right? M1 and M2. So yeah, there's the other place I'm looking for. It has the lift block 1. So there's all 3 of them. It has the lift block 1, so I'll call it M1GH. So that does an energy. So I can't just write H because now I'm mixing and matching. There's joules and there's meters. Right. It's got to all be joules, right? So plus your 1/2 M1V squared plus 1/2 M2V squared. Okay. And is that the same V? It's the same V, right? It's the same speed. I mean, different directions, but the same magnitude, same speed. Remember, energy is a scalar value. We don't really care so much about directions. Okay? Something else we don't care about so much. You guys know I haven't really written anything about time, right? I don't say anything about time as a variable, right? It's another thing to, oh yeah, that's true. We haven't seen time in a while. Right? So we can solve this. I could, here. I bet if you did it the old way with dynamics, you could get an answer, and the new way of doing it would get the exact same answer. Let's just do the new way. Sum of energy at point A equals the sum of energy at point B. So we got M2GH. The fact that the large block can fall, that's supplying all the energy. And it's doing 3 things. It's lifting block 1. There's M1GH. Right? It gets the same H, right? One's down, one's up. It's the same distance size. Right? Plus 1/2 M1V we're solving for squared plus 1/2 M2V we're solving for squared. Okay, so I think here I'm going to subtract this MGH over. So M2GH minus M1GH equals 1/2 M1V squared plus 1/2 M2V squared. I'll factor out, I'm going to do double factor right here. Right? On the left side, I'm going to factor out the GH. So that's M2 minus M1 and then GH. On the right side, I'm going to factor out a 1/2 and a V squared. So that's a 1/2 M1 plus M2 and then a V squared, right? Sure. Okay. And then multiply both sides by 2, divide both sides by the sum of masses, take the square root. So V, here, I'll throw in one more step. So V squared could be 2 difference of masses, GH, divided by sum of masses. All right, and the last step is square root. So the speed of point B is equals square root 2 minus M1, GH, all divided by sum of masses. There you go. All right. If you ever had a textbook question where they told you what the masses were or what the height change was, if you wanted to just solve that numerically, you could plug in the numbers at the beginning. Right? We've got the answer in terms of variables. So you can solve like any of these Atwoods. Right? And also you can find proportional changes. So for example, if you let this go like 10 centimeters, okay, great, it's going at some speed. But what if you let it go at 40 centimeters, which is like 4 times the height change? Guys, 4 times the height change is going to be how many times the speed change? What's the square root of a factor of 4? Twice as fast, right? Okay, the m's don't cancel because they're like subtracting on top and adding on bottom, right? So you can have any combination masses. You could test specific masses, see what happens. But let's do it. Let's run some tests. What if your M1 is just 0? You just have an empty string on one side and then all the weights on the other side. Would that be pure free fall? Let's see what that looks like. If M1 was 0, this would go away. M2 over M2 at that point actually you could cancel out. And, oh, you get square root 2GH. Look at that. Just like Galileo dropping stuff off the tower. Right? Yeah, so yeah, you could play around with that. Next one. A spring fires a ball vertically to its maximum height. Ooh, what do you think is going to be in the system? Yep, exactly. Ball, spring, earth. Right. Looks like this one, the next one, or about like that. Right. I think bell's about to ring, so I'll pause right there. That's about as far as I've been getting all day anyway. All right, so tomorrow we'll probably finish this. All right, got some challenge questions coming up for these last 2 rows. Right. And yeah, how do you guys think you did yesterday on that? Pretty good, do you guys think? All right. Let's call it a wrap on today.